You guys know what is the schedule, the second midterm written on the syllabus? No? No? It's in November, right? It's in November. Yes.
That good or that bad?
It's good. You don't need to worry. I don't think I'm going to give an exam. If I do, probably the end of this month. You know, yeah. The second midterm, yeah. Or beginning.
Okay.
Alright, okay, let's start. Okay, so we're still on chapter 5. And I'm not going to finish this today. And I doubt I'm going to finish on Tuesday. So this week and hope next week we're still on chapter 5. Because this is a very important chapter. There are a lot of technical stuff in this chapter. I do want to take my time. Okay, so which means the homework, the graded homework due for this chapter will be sometime next week, the end of next week.
Are you gonna sign it soon then? Or you're saying you're gonna sign it?
Yeah, I'm going to sign it. Yeah, I'm going to sign it soon. But it won't be due until the end of next week because by then I can finish everything for this chapter. Okay. Just to give you that. Okay. So again, this chapter we're going to talk about 3 different decision makings. And one is on the inputs. Then we're going to talk about outputs. And then the last decision making we're going to talk about is on scale, optimal scale. And we still have not finished the decision making on the input yet. Okay? And the analysis on this one, I have introduced you the production function. Okay, I've introduced you what is marginal product labor and what is marginal product of capital goods. Okay, and also the graph of those concepts. In last class, I introduced you how do we utilize the graph to find out the optimal input level. So I introduced you a line and a curve. What are those? Don't look at notes to see how much you remember. ISO cost and ISO quant. What is ISO cost? ISO cost is a line or curve? It's a line. It's a straight line. And shows you the total cost is the same, remain the same, right? And then we talk about the ISO quant. What's the meaning of ISO quant? Output remain the same. Okay, what's the shape of the ISO quant? It could be a straight line, could be a curve, right? Okay, and when is the case that it's going to be a straight line? That ISO quant is going to be straight line. What the production function looks like when the ISO quant is going to be a curve, it's going to be a line. What's the production function look like? Linear. Okay, it's going to be a linear function of K and L, right? Okay. Linear production function. Q is equal to such as 4K plus L. That is linear function, or linear production function between output and input. And if this is a production function, our ISO quant is a straight line. ISO quant is straight line, right? Okay, so there's one production function we talk about. Then we talk about another production function, and it's going to give you a curve for the ISO quant. What is that? Cobb-Douglas function form. What's so funny here? What is so funny here?
They impressed us.
Yes.
Okay. For example, K half power, F half power, and that will be a Cobb-Douglas function form. And the ISO quant is going to be the third function form, production function form, but I really did not go into the details of it. Okay, so we're going to talk about that. But I want to give you a little bit intuition about these two production functions, then we're going to go into the third one. So when a production function is linear, what does it mean? What does it mean intuitively? What does it mean? Go ahead, Chase.
Straight?
Huh?
I think straight.
Intuitively, what does it mean? So what kind of production process we are referring to when we have a linear relationship between output and input? Okay.
Constant.
When we have a linear function form, this implies that there is a perfect substitution between the capital input and labor input. For example, you can use okay, so let's say we have Q is equal to 4. Okay, Q equal to 4. And for Q equal to 4, you could have the input, which is L equal to 4, and K equal to 0. Or you can have an input combination K equal to 1 and L equal to 0. Okay? So when it's linear, you can substitute all the capital input by labor inputs to produce the same amount. So which means you really do not need both capital and the labor input in order to produce this good. So that's what we call the perfect substitution between the labor input and capital input. Okay, so this kind of production is referring to the production of goods that is low technology intensive. Yeah, because you really do not need the machine to do it. The humans can do it as well. Okay, so there's a perfect substitution between the labor input and capital input. You don't need, you can just use one input or the other. But for the Cobb-Douglas function form, you will need both. You would need both capital and the labor input in order to produce. There is some level of substitution, but it's not perfect. You cannot just substitute the capital with labor altogether, totally. No, you cannot do that. You will, in order to produce this kind of good, it requires both kind of category of the inputs. Okay, so that's the Cobb-Douglas function form. It has some level of substitution, but it's not perfect. But this one is a perfect substitution between the two inputs. Okay.
So, would you say like a small business would use the linear production function, and like a big firm would use the Cobb-Douglas function?
The goods requires more technology.
Right.
Wood tends to have Cobb-Douglas function form.
Okay.
The goods require very least amount of technology.
Yeah.
You know, making food.
Yeah.
It requires very little technology to making food, cooking, right?
Right.
Somebody can cook at home, produce the
Sure.
same kind of food, right? So that tends to have this kind of linear production.
Okay.
Tends to, okay? Still, and it does not mean it will absolutely be, definitely be linear production function. Okay, so third function form I'm going to introduce, you call the Liouville function. Liouville function. The form of the Liouville function is like this. Q is equal to mean between this number and this number. Okay, what does it mean? If K is equal to 2, L equal to 3, this Q will be the minimum number of 2 will be equal to 2. Okay, so the production equal to 2, if K equal to 2 and L equal to 2, or or 3, or 4, or 5. So which means that the extra labor, that more than the number of the extra labor provided does not serve any purpose in the production. Okay. Let's draw this graph, then we can talk more about it. What the graph looks like.
So the number K would not
There's
always dominate.
No, nothing is dominant here. Okay, if the L is equal to 2, K equal to 2, then this is 2. If L equal to 2, this K equal to 3, this still equal to 2.
Oh,
Okay.
So smaller is paid in the row here.
That's right. The smaller number means the smallest one.
okay.
The smallest number of these two is going to be the output.
And that's it? That's how we solve that?
That is a particular function form. We call the relative.
Okay.
Okay, so we're going to talk about what does it mean here. What does it mean here? Can you think about the meaning of it? But first, let's draw a graph. Okay, when Q is equal to 1, let's say Q equal to 1. What are the possibilities here?
Yeah.
One or
1, K equal to 1.
Uh-huh.
Okay, K equal to 1.
L could equal to
L could be equal to 1.
Or 0.
just one.
No, it cannot be 0. Because L, if L is equal to 0, this will be equal to 0. Right? So when Q is equal to 1, K equal to 1, L has to be greater or equal than 1, right? Okay, so how do we draw this? K equal to 1, and L is bigger or equal than 1, so it's this line here. Correct?
Yep.
Yeah.
Okay, so that's one possibility to give output which is equal to 1. What is another possibility that will give the same level output which is equal to 1? Is when L equal to 1, but K is greater or equal than 1.
You draw a straight line up.
That's right. So the graph like that is going to be, okay, so this is now is our isoquant. This is our isoquant. So if you choose any point along these two sections, okay, you're going to produce the same, and which is equal to 1 unit. Okay. Another isoquant will be here, will be equal to 2. This is the isoquant which that's going to produce 2 units. So what this function form tells you that there is a fixed proportion of the inputs. Fixed proportion. In this case, 1 and 1. 1 capital and 1 labor input. That's a fixed proportion. Okay? So it's the same, you have to have same amount of capital and labor input produced. If one input level has an extra, then that extra just useless. Okay, so this function is a very particular function. You do have to have the same amount, okay? But we can change this, okay? We can change this into 2K L. And it's still the fixed proportion. It's just the proportion here is going to be a half and a 1. But it's still the fixed proportion. It still tells you that, you have to have this proportion of the labor input and capital input. Anything extra is going to go waste. So in this case here, we talk about substitution here, right? This is a perfect substitution between the capital and the labor. This is a some level substitution. But this one, there is no substitution between the capital input and the labor input. You cannot substitute labor with capital at all. There's no substitution whatsoever.
And then that second line is just if Q is equal to 2?
This is Q equal to 2.
Okay, alright,
This is
So-
Q equal to 1.
got it.
Okay. So the higher, you're going to have a higher level of output.
Sure.
Okay, so perfect substitution between two inputs, some level of substitution, and there's no substitution.
Can you like verbally walk through a scenario in which you use that, like an example, a business example? I'm not
This,
sure what
this,
the concept
actually,
is.
this, you're talking about the example of the production particular, right?
Okay,
Is it what's your question?
I think so.
Okay.
Yeah.
So the, actually, this production function is very, very hard to use, hard to find. Okay, very, very hard to find. The book gives the example, which is, I'm not too convinced. Okay, so use the blackboard and not blackboard, keyboard. Okay, let me. Okay, so they say K. You can single K as a number of keyboards. Okay, and L as the number of keyboarders.
Persons using the keyboard?
Yes,
Oh, so
Okay.
you can't have more than 2 people using one
is-
keyboard.
that's right. So you have to have a keyboard and one person. If you have next person, that person they just go with.
Okay.
I see.
I'm
Yeah.
understanding now.
Yeah.
Gotcha.
Okay. But it's still not really a production, but it gives you the idea. So there's no level of substitution.
Okay.
Okay, so this is the 3 different function form talk about. And due to these 3 different function form, we're gonna have different isoquant curve or line. And this one is neither curve or neither line. Okay. All right. So in order to find optimal inputs, we need to combine the isoquant with isocost. And I gave you an example last class with this linear isoquant, right? We went through an example. You guys remember?
Is that with the,
Yeah,
Okay.
I asked you guys to
Yeah.
do it. They have 2 different slope, right? Isoquant has slope, isocost has a slope, right?
Mhm.
So eventually you're going to choose either
The
all
linear
of the
side.
labor or all of the machines.
right,
Right? Okay, so that's how you find optimal inputs for this case. So in this case here, the optimal input is always here or here.
right,
Okay, it's narrow in between. Okay? And in this case, the optimal input will be somewhere in the middle. So which means you will need both capital and labor. Okay, how about this case here? If we add isocost into this picture here, where do you think would be the optimal? Of course, we don't have the isocost, but you have to imagine. Now we're going to put the isocost line there. So
Oh,
where
th-
would be the optimal input level?
this is just a guess, but you would have a tangent line to one of those corners.
So which point will be the point they meet?
2 and 2 be higher production.
Will be always those points here, right? So it
Yeah.
does not matter what's the shape of this isocost line.
It just has
Eventually,
to,
yeah.
yeah,
Gotcha.
right,
Eventually, it's always going to meet this corner
Sure.
point. Okay, so you know the optimal input is always is right here,
Mhm.
either here or here. Oh. Okay. Depend on the output level. If you want to produce 2 units, will be here. If you want to produce 1 unit, will be here. Okay. So any question about here? So I introduced 3 different level production function to give you 3 different isoquant and show you how do we use a different isoquant to find optimal K and optimal L. Okay? And you have homework problems, I think, for all of these 3 cases.
So
Yeah.
the K to a half and then L to a half. That's the Cobb Douglas.
This is the Cobb-Douglas function, it's
Yeah.
like this.
it's the one with the derivative.
Right there with the included lines touch, that's the optimal on the Cobb Douglas.
It's, yeah, so it's always like in the middle.
Yeah.
Okay, so which means the optimal input will have some level of K have some level of L. It requires both. But in this linear, no, you don't need. You either use all capital or you use use the labor. And here you use only at this corner point.
On the Latif, if the price line isn't enough to meet the second level,
What do you mean it's not enough to meet second level? The slope can be anything.
okay. I see.
Does not matter the slope is. And it's always meet this corner point than the other points.
Okay.
So K can be like way up there, the labor could be like way down, right?
Yeah, but it's always a corner point.
Right.
Yeah.
So for the Latif function, they give you you said something about they give you a set, like you have to get a certain amount of like K and then a certain amount of L, right?
L, that's right. So look at this example I gave to you here. K and L. Okay. So if this is a relative function form, then which means if you have capital good one machine, then you have to have one person. If you have two machines, you have two people working. You cannot have 2 or 3 or 3 or 4. No, because the astral line you just use this. So fix the proportion. Okay, fix the proportion. Yeah. Okay, so any other question on this stuff here? Good. And also, so when we talk about this function form here, actually, Cobb-Duck this function form is the most useful one because majority of the production fall into this category, which means require both capital and labor, and there's some level of substitution, but not completely. Okay. And when we talk about this isoquant curve, as we derived a condition for this. Optimal input. The condition is you guys remember that?
Mm-hmm.
So that's the condition for this optimal input level. Okay, and we know this is the slope of the isocost line, and we call this is a marginal rate of technical substitution. Marginal rate of technical substitution. Okay. I'm RTS. So this slope here is marginal rate of technical substitution. And this two has to be the same. Okay? So I think that's what we have learned so far on this. And there's still one more small concept that I have not introduced for this section. Okay? But let me show this stuff. Okay, so I'm going to use the question homework problem 1 to show you this concept. I think homework problem one I show you how do we do part B, right? Last class we did part B. And part A we can talk about later. It's pretty straightforward, just calculation stuff. And part C tells you this, okay? If you can sell the output at the price of P equals 200, okay? And also you can hire labor at $50 per unit. And they ask you how many labor you should hire.
This is, I'm sorry, what question?
Question one, homework 1, and is part C. Okay. And the function form here is this. So this is called Douglas function form they give to you. And also they also say assume that capital is 81. Okay? So that's all the information you have. They ask you to find this L. Okay? So they ask you to find this L star. And knowing that K star already equal to 81.
Are they both supposed to be K out there?
It should be
No, it's
L.
supposed to be L.
Thank you. It should be L. Thank you. Good.
3, 3, 1.
Actually, it's question 1. Question 1. All right, we did part B. Okay, we derived what is MPL. Okay, so we're gonna do this. Okay, so if we look at the graph here, we know the K star is 81. Okay, the book already tell you, and then we're looking for this L star. Okay, to find this point, we have a formula. We do have a formula. Okay, but are we able to use this formula to figure out the L star? And why? What is missing here?
The isoquant. Well, no, it's the isoquant one, isn't it?
Let's have all this to get. Let's derive all this first. Okay. Okay. MPL. I showed you is a derivative, partial derivative of the output with respect to L, right? We did this. Let's repeat this exercise here. So we take the derivative of this whole thing with respect to L, and then we treat K as what? Constant number, right? Okay. So what will be the derivative of Q with respect to L? Okay, we did this.
4. It'd be 4.
What are we gonna do? What are we gonna do with this part?
Copy.
Disregard it.
We don't discard it. We keep it, but we take it down, copy it. Because now we treat this as like a constant number.
Okay.
We just copy the part down. Okay? Like a constant number. And then we're gonna take the derivative of this now. It has power, quarter. So we're going to bring the power down, right? Yeah. Okay? Bring the power down. Then we're going to give it a new power for the L, which is equal to what?
Minus.
The original power minus 1. Okay, that's the formula. Okay, I gave you that formula as class. Okay? Whenever you have something like this, take the derivative of this variable, you take the power down, then the new power is this original power minus 1. Okay? So it will be minus 3/4.
But you don't do anything to K?
You gotta multiply it.
No, when you take the derivative with respect to one variable, you treat the other variable like a constant value.
Okay. So where'd you get the 2Q over 2L?
It's not 2, this is a symbol like a
Derivative?
theta, derivative, partial derivative symbol.
Oh, I've
Right,
never
it's
seen
not
it.
2. Yeah, it's just, looks like 2.
Yeah, it does. Don't it?
So everybody is clear about this derivative here.
Okay.
Yes?
Where did you get 3/4 and 1/4 from?
Okay, so you bring the quarter down, right? Then the new power should be this old power minus 1. What quarter minus 1?
No, that's not what I'm asking. I'm asking like, how did you get like K to to the 3/4 power? Oh, it's okay.
This is something we're now going to treat as a constant number. When we take the derivative with respect to L, the other variable we treat as like a constant number.
Okay.
We treat this like a 2 or 3 or 4.
Sure.
When we have a constant number, what do you do? Constant number multiply variable, we just copy it down, right?
Right. Yeah.
So that's what we do. We just copy it down here.
And that's already given.
Yeah.
That function is already given.
Got it.
Okay, so if you got this, then let's do MPK again.
So it's
Okay,
with
you should
respect-
be able to do it now. We're taking the derivative, partial derivative with respect to variable k only.
So L is the constant.
So we treat which one as a constant now?
L.
Okay, so how we're going to do with this L quarter?
Bring it down.
Bring it down.
Bring it down, right?
Mhm.
Okay. And what we're going to do is this k is three quarters
Bring
power.
the 3/4 to the front and then
Bring the
subtract
3/4 down. And what will be the new power for the k?
one.
Minus 1/4.
Minus a quarter, right? So is everyone clear about this now?
Yes.
Good. All right. So we have the formula for MPL and PK, right?
Mhm.
Okay, look back this condition for the equilibrium because we always want to use condition, the optimal input condition. Okay. We have MPL, we have MPK, the expression of it. We can do what? We can divide it. And looks hard, but it's not really hard actually. Okay. So let me make it easier to see. Okay. Anybody can simplify this ratio for me? Is it from what class? Calculus class 2?
Yeah.
So a quarter divided by 3/4, what's that equal to? Look at this part.
But you,
It's
on
gonna
the
be
top one, you said a quarter L. I think. See, you
It's
got a
gonna be
quarter
1/3.
K to the 3/4.
It's gonna be 1/3.
That's-
Like Paul back.
That's
1/3.
1/3.
a coefficient, it doesn't matter which one it's from.
What is equal to
It's
first?
1/3.
Are you sure? Are you sure?
Yes.
Yeah.
Because you have to do the reciprocal and multiply it. Is that correct?
It's like this is a quarter. This is 3 times quarter. 1/4, 25 cents divided by 75 cents is what? 1/3.
1/3, yeah.
I have to use that, right?
It helps.
That helps,
Yeah.
right? Okay, so now we're going to deal with the k, the power for k.
Subtract
So on the numerator, the power is 75 cents. And on the denominator, the power is minus. This is not a good example for this for the money. It's just 3/4 and minus quarter. So so eventually what's going to be?
-1.
1 or -1?
-1.
It's 1. You
You
subtract
add it, cause
negative.
it's
Yeah.
3/4
Wait,
minus
hold on.
a negative.
So it's
1/4.
this
I'm
one
looking at the
minus
L.
this one. So you're going to be adding up together. So it's equal to
Oh.
1, right?
I'm looking at the. I was looking at the L.
Good. Okay. So then we take care of this. Now they take care of this L. Minus 3/4.
That's gonna be -1.
That will be
So
negative
you
1.
put the L on the bottom.
That's right.
0.
Good. You got it.
All right.
Okay. So after we simplify this, what we have is k is on the numerator, 3L, and on the denominator. Correct?
Yep.
Do we know k? Do we know the value of k?
Sure do.
Yeah.
It's 81 units. That's already given. Correct?
Yep.
Okay. So we plug right into here. 81 3L. Okay. Everyone is with me here?
Yes.
Okay, good. So we already have a very simple, simplified form for this marginal rate of technical substitution. This term here, right? Okay, if we have the value of the right hand side, which is slope, of the ISO cost, then we'll be able to solve L, which is our goal here, right? Okay, now, let me ask you, do we know PL, which is a wage for labor?
Yeah.
Yeah.
50.
50. Do we know the price for the capital?
No.
We can get it though, can't we? Oh no.
They don't have, they did not give us. We do not have that. So even though this condition is the most useful condition in this kind of situation, but we don't have all the information we have to solve L because we do not know this. So we cannot use this approach. But I go soon through this because for some problems, you will need to use this approach to do it, okay? But in this question here, since PK is not given, we cannot use this. But there's another information that is given. What is it? We have not used
The
yet.
price,
The price of this good is $200.
right?
So when the owner of this manufacturer, after they produce it, they can sell in the market for $200 per piece. How are we going to utilize this information?
Wait, so, but then the cost of labor is 50, so when you subtract it? Or,
It's not that simple.
oh,
It's not that simple. I want to give you a few seconds to think about how we utilize. We have always, the stuff we have been talking about is always, the price of input. When the price of input is given, and we're able to figure out the input level. But now, one price of the input is not given, but the price of the output is given. How do we solve it?
Oh, is that the the formula equal 200 to find out the?
This is a price.
what about
It's
K?
not the output.
What about K? K is
It's
81.
not this.
Does it have to do with K? Like, am I on the right train of thought? if I
We
use K?
will not need K anymore because K already has 6 number. We will
Wait,
not.
so we don't use K at all to find
L.
P or PX or PK?
We will not be able to find PK.
Okay,
We will not be able to find PK.
gotcha.
So how we do it? We're still going to be able to find it with just this few information. I want to ask you a conceptual question here. Okay, so all this information here is input. Okay, input information. Price of the input, the quantity of input that we're looking for, and then we have information about the output. That is two different sides of the market. The input market and the output market. The market interact, they're connected, they're not separated from each other. So what is the connection between the input market and the output market?
Consumer.
The point. What is that connection?
The transaction itself.
And let me give you another hint here. We talk about marginal analysis. We talk about that? Marginal analysis?
Yeah, I think so. Maybe.
Marginal analysis? I think at the very beginning of the class, maybe it's the first lecture. Very first one, I introduced myself, you introduce yourself, then I did mention the marginal analysis. It's a concept. What's marginal analysis? Okay, you don't worry about it, I'll tell you here. The marginal analysis is the most important principle in microeconomics. What it tells us that it does not matter what decision you're talking about. It could be the decision by the consumer, or the decision by the producer, or the decision by a policymaker, or the decision by an entity, by industry. No matter what decision you're talking about, the optimal decision always relies on this one condition, which is called marginalism. And this one condition that the marginal benefit of that decision must be equal to the marginal cost of that decision. that is marginalism. So in order to solve this question, that's what we can use. The marginal benefit of selling one more unit must be equal to the marginal cost of selling one more unit. Okay. So now, how do we use the marginal analysis here? When we want to produce, so since here we're talking about the optimal input. So instead of asking what is the marginal benefit or marginal cost of producing one more unit, we can change the question a little bit, kind of step down one more level, ask this question. What is the marginal benefit and marginal cost of hiring one more worker? Okay. If we hire one more worker, what will be the cost of it?
$50.
Good. So that will be the marginal cost of hiring one more worker. Now we're going to say what is the marginal benefit of hiring one more worker. Okay? We know the capital good is fixed, right? So capital good is now changing, it's 81 units. So when we hire one more worker, what will be the additional revenue that is generated by this one more hire?
50 plus 81 minus
Additional revenue is equal to what? Say it again.
Yes, 50 plus 81 minus 200, right? Oh.
The additional revenue due to this additional worker hired. So to answer that question, first you have to know, when we hire this one more worker, what's the additional output that's going to produce, right?
Right.
What will be the additional output that's going to produce?
200.
What is that? Additional output when you hire one more worker, what is that? You guys know this. The addition.
MPL.
That's that, right?
Oh.
When you hire one more worker, that is the marginal product of labor. That is how much more output it is going to produce. If this much more of output is going to produce, and each output, you can sell that at $200, then what will be the total additional revenue generated? It's 200 multiply that.
So we played 200 into.
So would be P multiply this.
Okay.
Okay, let me repeat what we're doing here. So what we use is a marginal analysis, marginalism concept. Marginalism concept is marginal benefit of decision must be equal to the marginal cost of decision. And the decision we're talking about is how many workers to hire. So we're interested in hiring one more worker, this simple decision. So when you hire one more worker, the cost is $50, you have to $50 more. And when you hire one more worker, and you're gonna have more output generated, and that more output is represented by MPL. And that more output, you can sell that output at $200 in the market, and that's the total additional revenue generated. So this represents the marginal benefit of hiring one more worker. And this is the marginal cost of hiring one more worker. And both is dollars, you send them equal to each other, and you can solve L. Okay, so now let's see how we do it. And we already know MP. Okay, so we already know MPL is this expression here. It's K3 false. Is this? We just plug 81 into here. Okay. When we plug 81 into here, that's going to be equal to 27.
Yeah.
27. Use your calculator. That should be 27. So 27 divided by 4 multiply L 3/4. So this is your MPL. Now, P multiply MPL is equal to $200 multiply this. And this has to be equal to the $50. So in this equation there, you only have one variable L, then you can solve it. But don't lose in the calculation. Remember this. If you remember this, you can always get it right. It is marginalism constant. Marginal benefit of decision is always equal to the marginal cost of decision. And this decision we're talking about in this question is hiring labor. So we're interested in the marginal benefit of hiring one more worker and marginal cost of hiring one more worker. Even though it's kind of a little bit technical and complicated, but are you guys following me? Most
Yeah.
of the
And then how'd you
solve it.
how'd you get 27 again?
Actually, I use my head to
Oh.
do this. You just use your calculator.
Yeah.
Plug 81 into this, then the power is 3/4.
Okay,
You should get 27.
got it. Okay.
But to me, is calculator is harder to use than myself. So I just. It is true. When I was in college, we do not use calculator. We do not have the fancy calculator like you guys have. We have to use by hand. Use calculation by ourselves. So that's why you give me a calculator. I may not know how to use it. Well. Okay. I still figured it out. Okay. So. We can solve L, right?
Okay.
But I'm going to solve it right now because you may still have a little bit difficulty in solving this. Okay? So, what I want you to do is, when you have something like this, you want to simplify it. How to simplify it? You want L on one side, the number on the other side. Okay? So L minus 3/4 is equal to 50 multiply 4 divided by 200 multiply 27. You use your calculator to do this. Okay, so what I'm doing here, you may not follow here. Okay, so to get rid of 4 here, I multiply 4 on both sides. Then I divide 200 on both sides, get rid of this. Then I divide it by 27 on both sides, like this. Okay. So eventually this will be 200. So 200 cancel out, it's just 1/27. So L minus 3/4 is equal to 1/27. You guys have the sophisticated calculator? Somebody has it? You do.
Huh.
Go ahead, calculate L, use the calculator. Okay.
Yeah, I got you.
You all have calculator to use?
11.84.
Huh?
11.84. No? I did it
Not
wrong.
correct. You see, that's why I want you guys to do it, because it's, even though does not look very difficult, but okay, she has one. Now try it out yourself.
I did it backwards.
Did you have to take like a law or alien, national law or something? Because it's an exponent right there?
In the calculator, you have to do that. Yeah, but if you do it here, I'm going to show you to do it by hand. You don't have to do it. Yeah.
Alright, so we're doing.
Yeah, I think the national law is the exponent.
Huh. Alright, how do you get rid of the, how do you transfer over the, negative, 7.5 root, whatever, exponent?
Well, take rid.
How do I transfer that to the other side? What do I do?
Hello. Question. Okay. So if I do it by hand, that's what I'm doing. Okay, pay attention to me. That's what I'm doing. I'm going to give it a new power, multiply new power.
There you go.
Minus. So minus, they eventually cancel out with L, right?
Gotcha.
So then the other side, you're going to do the same thing. Right? Okay. So now we don't have to worry about this. This is just 1 now. So it will be just L. So L will be just equal to that.
81.
It's 81.
Still.
Yeah.
I have the
Let me see.
never mind.
It's 27, 3. Yeah, it's equal to 81.
So,
Yeah.
81. Alright.
Okay, it's a big question. No, it's a long question. When you do this, do it on a piece of paper. You know, in a Connect Plus, they just ask you put a number there, but you do all this procedure there.
81.
It should be 81. Yeah,
27.
yeah, it's 81. I'm pretty sure it's 81.
It is.
Thank you.
Let it out. It's not comfortable. Any question on this? If you get, let's say, 70% of this, that's good. And the rest of 30%, you go home, practice this problem, then you will get the rest of it. Okay. But if you only get 30% now, then ask me questions.
My brain is fried like that chicken nugget.
Are you fried? Your brain?
Go home for
Right.
A second.
Out the window.
What's that? Question? You want to take a break?
yes.
Until next week.
Who's that? See me next week. Who's that?
To the.
That was him.
Oh.
Johnson.
Oh, it's 2. Wow.
Alright. You know, there is a homework problem. It's very similar to this one. It's question 13. Okay? And I may put that question on the midterm. Second one.
Question
Question
13.
13. Question 13.
You got it.
Okay.
On this upcoming homework?
Not homework. It's yeah, I think it may be on the homework too. Yeah. And also will be on the midterm. That's what the kind of question I'm gonna give you. Anything else you want me to go over here? That's it. It's good. I'll let you guys go early because I think it's a lot of stuff. But okay, hold on a second. He has a question.
It's 27 to the 4
4/3.
4/3, right?
Yeah, 4 divided by 3. Okay.
So that's the power.
Yeah.
This is the
Oh.
power of 27.
How did you get rid of the negative?
Okay. Nobody will not pack yet. Somebody asking a question. How do I get rid of this negative? In order to, what I want is get rid of all of this. To get rid of all of this, I multiply this by this.
Yeah.
Then if I multiply this by this, which means I add the power to this term, I have to add the same power to the right hand side as well. Okay, so that's how I get rid of all this stuff.
And how did you change from 1 over 27 to 27? Because I think
Which
it's
one? Good question.
because I mean it's still the
Question.
same.
Yes, look at here.
Yes,
minus.
negative.
This is positive.
Oh.
Minus
Oh, I thought there was still negative there. Okay.
This is negative, this is positive. I just flip it.
Okay. Yeah, I thought I missed. I didn't see. I thought there was a negative still in that. Okay.
Guys, I flipped it. Yeah.
Okay.
Awesome.
That's stop thinking when you go home. I say, for after a couple of days, you're gonna have new understanding of this.